looks like we are recording. So next Thursday, I believe, is our midterm. So there are already, or should be up there, 2 practice midterms with solutions. So this is my basic advice on practice midterms. I take the practice midterms as if it was an actual test. Give yourself the same time as you would have in a class period, and, you know, restrict yourself also to just a couple pages of notes and things of that sort. So you kind of reproduce it as much as possible. Don't look at the solutions till after. The solutions are kind of work solutions. I try to color code my answer things in all red so you can just kind of follow them along when you go in. So it should help you work through them. And just give yourself like a day or two between each one when you do it. Like try one. That way you can kind of get some feedback. You can kind of think about it, and then you'll see how well you do on the second one. Now, the other thing I'm willing to do is to have what I call a study session. We can either try to arrange a spot where we all get together, we ask questions, or I can do it as a virtual event. I don't know what's easier for all of you. In non-COVID times, I would just have everybody together in one spot, but I realize it's not always easy to do that. So I'll leave that up to all of you right now. Does anybody have a preference in person or online for a review session? In person is great. I think it's usually easier, but you know, sometimes it doesn't always work out as well. All right. So if the test is on Thursday, best time for a practice would be Wednesday. Let's see if there's. Yeah. I'm forgetting to get a new blue pen. I'll leave. Tuesday is the class day, so I'm not as big as putting them on there. I think the closer it is, theoretically Monday might also work. Essentially, we have 8, 9, 10, 11, 1, 2. All right. So 11 to 12 does not work well for me. On Wednesday, this next Wednesday, I have a meeting there, and I have an 8 o'clock meeting, and then about 3. Oh no, actually next week I don't have to pick. My daughters are on vacation, spring break, so I don't have to pick up. So I do have all the way to 4. So those are my no-go times. So the way I do this is, if you have like a no-go time, you cannot do it. We'll see if we can get one Wednesday. They're best the day before. Diminishing returns the further we go. Does anybody have any no-go times on Wednesday?
There's the lab on Wednesday from 2:30 until 5:30 on both Wednesday and Monday.
Any other no-go times for people?
I can do it on 1:30.
You can't?
Yeah.
1:30 and on? Any others?
11 to 12 on Tuesday and 2 to 4 on Tuesday.
Oh, 11, 12. Here? Yeah.
And 2 to 4.
And 2 to 4? Well, that's kind of us, right? On Tuesday? So, yeah, we won't schedule. So one thing we could do, right? This one I usually run over a little bit. That's lunch with my son. So we could set up a time here, if that works for people. My only fear was sticking, this is also a fairly good window, but this is like right before class. And there is kind of like diminishing returns. I mean, I love this stuff too, but I think after 4 hours, you might hate me. So I don't think anybody wants to hear anybody talk for 4 hours. So, yeah.
I can't do like 4 o'clock on Tuesday or like 9 to 12-ish on Wednesday.
Okay. So, yeah, so 9 to, so that's kind of, actually, that would be that whole thing. So, but this would potentially be okay for you.
Yes.
All right, and then that slots out. All right. So we could do like an hour here, or we could take a 2-hour block. But like I said, you might get sick of me. So, yeah, that's kind of. Joshua, you're not hurting my feelings. Like I said, I don't think pretty much anybody wants to hear anybody for 4 hours. So do we like the idea of this a 1-hour block?
That's good.
Okay. So I will try to get that one scheduled. It'll probably be about 12:20 or so. Give me time to walk over here from Penland. All right. There we go. So, sorry, my pen is starting to ooze out the side. I always hate that. Get ink on your fingers. Okay. Let's go to the next topic here. So there's a few topics basically left if you look at the breakout, right? We're going to talk about a couple different new design techniques today and a few specialty devices. And then the next time we'll talk a little more in depth about how you can do good jobs with basically doing behavioral testing and things like that with Verilog. So you can kind of understand some of the ideas a little more in depth. All right, so let's start out with some of the ones that we're going to talk about today. The first one that we're going to do, so well, actually, let me give you kind of an overview. We're going to talk about decoders and encoders and mux, right? There's technically also a demux. I'm going to put my emphasis on these two because they're the most useful. But there are some cool things we can do actually with this combo also, decoder, encoder. All right. So let me start off with the simplest device called a decoder. So a decoder is just as its name says. We get a code that comes in and it breaks out the code for you. Now this is electronics style encoder, decoder type stuff. So when we're talking about codes, we mean binary. So I send a code in. So the device looks like this. And I have a code. Let's say it's n bits. All right, so if I have an n-bit binary number come in, that means it's going to cover basically a total of 2 to the n values. All right? It's not too sure, right? If it was 1 bit, you would have a single bit. It could be a 0 or 1. All right, so 2 to the 1. If you had 2 bits, it's saying that you have 2 numbers that you can put in. All right, both of them could be 0, 1, so you'd have 4, 2 to the 2. So on and so forth. So that's why we say 2 to the n. So I've got some number come in. Let's for simplicity's sake just say that I've got 2 bits coming in here. We don't lose anything of the idea, but just realize it can scale as big as you want. I just don't want to draw that many. So this would be, we're going to call this the 0, 0 spot, the 0, 1, 1, 0, 1, 1. So I've got these coming in, and I've got a line that comes out. And these lines are going to tell you, was it this code or not? So in this sense, this is the code. This is 0, this is 1, 2, 3. So a code comes in, and I got a flag that comes out that tells me which code it was. Does that make sense? That's why it's called a decoder. Now, it's a fairly simple device in order to build this. Right? Sometimes we also have what's called an enable, basically an on-off switch. We don't always show the enable, but you can put an enable in as an added feature. I'm going to ignore the enable for my initial design, and I'll show you it's really easy to add the enable in. Let's consider just how I could do this first one here. All right, I've got 2 bits that come in. I'm going to kind of increase the size of this a little bit. I'm going to break this into 2 bits, right? These are the individual 2 wires coming in. And I want to know if both of them are 0. In order to activate this, it's the number 0 line. That make sense? So how can I check and see if both of these are 0? Well, I've got these 2 wires coming in. Let me just call them, this is my, code bit 0, code bit 1. That means I've got a table, code 1, code 0, and I've got line 0 coming out. When it's 0, 0, I want it to be a 1. On all the other ones, I want it to be a 0. Make sense? What'll give me this truth table response? All right? Yeah, whenever you see a single 1, think and. All right? So this is an and in order to get a 1 here, I have to negate both of the inputs. So I have a single AND gate coming out, and I negate both of the inputs. Done. All right, that's all I need to be able to build it. What do you think is going to happen with the 0, 1? All right, that's an output over here, that's 1. Output 1. It needs to activate when 0, 1 is given. In all the other cases, it wants a 0. Guess what you got again? You got an AND gate. All right? So I'll just have another AND gate. And I only have to negate C1. But not C0. All right? So on down the line, right? You can tell each one of these is just going to be an AND gate. And you just put the negations in wherever you want the zeros. Easy peasy, right? What if I want to put an enable? Well, an enable would mean I want the code to come out if enable is true. Otherwise, it's a 0. So I would just add one extra thing here, right? This is enable is equal to 1. And if enable is 0, it doesn't matter what this is, it gives me a 0. Remember, X means I don't care what it is. It gives me the full options. So all the enable does is add this extra 1. Well, notice it still has a single 1 on, so it stays an AND gate. And it should only give me a truth out when enable is 1. So if you added an enable bit, all that enable bit's going to do is come up and just go to each one of these and add it in. You just AND in, and it's got to be always true for the enable. So it's just a slightly bigger AND gate. Now, there's several things about this. Decoders are blindingly fast. It's only 1 gate level. So that's kind of a very nice feature. It also breaks out all the possibilities. If you think about truth table, ignore the enable for a sec here. Right? Basically, 0 will give you a 1 when you have the min code, right? If you look, this 0 here is identical to our little min term 0. This 1 here is identical to min term 1. So on and so forth. So in essence, this is breaking out all the min terms. Now, decoders are used all over the stinking place. This is the primary way we build memories. All right, so later on we're going to get into memories, and you can imagine when you do a memory lookup and you send an address, I can have the address come in here, and it turns on the line for whichever memory address you want. So I can just send an activation pulse to that particular memory module. That's why they work nicely. All right, because I just literally send a code, hey, you wake up, you know, number 3, and it goes down to number 3 and sends a wake-up call. We'll worry about that in the second half of the course when we get into memory. I just want you to keep that in your mind. Decoders are really useful. But imagine for a sec here, I wanted to actually implement some other function. If I have a device here, a decoder, let me again, I'll ignore the actual enable signal. Let's say I had a truth table I want to do that had A, B, and C as the inputs, and some function F, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and whatever, you know, 0, 1, 1, 0, 1, 1, 0, 0, fair enough. I have whatever's going on here. I take a decoder. I have 3 inputs, so I pick a decoder that has 3 inputs. Zero, 1, 2, 3, 5, 6, 7. The decoder, therefore, will have 8 outputs, numbered 0 through 7. This input here for the 3, curly braces in Verilog concatenates things together, if you remember from labs. So I can just take A, comma, B, comma, C, put them in curly brackets. That makes kind of one bundled number out of them. That's my address line. So when ABC is 0, 0, 0, that corresponds to this line. All right? When it's 0, 1, 0, that's this line. So it just basically put them in the order and allows me to treat this truth table as my code. Now, if you remember, this is going to turn on the signals appropriate based on whatever this code is. Now, I want to combine this one here, little m1, and little m2, and little m4, and little m5. Those signals get lit up are this one, 1, 2, 4, 5. If any one of those turns on, that's one of my 1 outputs. We agree? So all I have to now do is take these, and we're going to OR them together. And there's your function. I'm done. There's 2 gate levels because this is generating all the min terms. And so 1 gate level here, 2nd gate level here. It is a perfect, fast implementation. This is essentially identical since it's memory. This is identical to what's called a lookup table. This is basically just setting the memory for the lookup table. This is actually what your FPGA does. It does a variant of this. It actually, let me flip the page here. Maybe. Okay, there we go. It takes that same code here for the decoder. Inside your FPGA, A, B, C, 3 inputs. 0, 1, 2, 3, 5, 6, 7. And now it has a little single memory cell that holds a value. And if this line lights up, it basically reads this memory signal and tells this one, send your value out. It says you've been accessed, right? And then they will send their value out on their output line. So these are essentially enables for these memory. Something's stored here. You send an enable line in. It's going to give you the value stored inside here out. And then I'm going to take them, and I'm going to run all of them into an OR gate. I'll use our array notation. And it just connects them all together. Only one of them can be accessed at a time because only one line is going to be lit up at a time. And then you can just actually store your truth table. In our case, it was 0, 1, 1, 0, 1, 1, 0, 0. You literally store the truth table in, and then you send the code down, and it outputs whatever the value is. And you get a 0 or a 1. Exactly at the time you needed a 0 or a 1. This is actually what you mean when you do a lookup table. All right? When people create them in software, they just create an array. This is an array data structure. And this is your index to the array. All right? In hardware, we actually just make individual ones, and we use a decoder to do the indexing. All right? So it's kind of our iterator that walks through them in whatever order you want. But this allows us to access them. So lookup tables are really actually a very good, fast way to access things. And that's in truth what happens when you're doing your FPGAs. They take all of your functions for an FPGA, they compound them down to a truth table, they break them up into reasonable sized truth tables, and they literally encode them. So if you look at that last stage, right, you walk through synthesis and then the layout and routing and all the rest. At the end, you get a file called a bit file. That's what this is. It's all the bits stored in all the lookup tables. And it just saves them to the right locations. And then when you run your FPGA, it samples them only at the clock intervals, the only time it's going to sample these. So it makes sure it has no glitches. Otherwise, it holds the value in between them. So it's basically your FPGA programming is just making one big clocked truth table. That's all it's doing. But that's legitimate hardware design. It's easy to fabricate, and away you go. You can build whatever you want. You reconfigure on the fly, you just load new memory. That's it. But it's a very elegant way to do it, and it's all enabled by these decoders. So what do you think would be the opposite of a decoder? An encoder. What would an encoder have to do? It would have to take, I'll give a decoder. Let's do a smaller one just for drawing's sake again. 90123. 2-bit code comes in, and out it goes. An encoder would have to look just the reverse. You'd have a bunch of lines that tell me which code do you want. Do you want the 00 pattern, the 01 pattern, the 10 pattern, or the 11 pattern? And then it would output a 2-bit code for that. All right? This decoder is extremely useful, and it's very well defined, right? You tell me whatever code, I light up the light. How about this encoder? Does this look like it's pretty well defined? Right? You turn on, you hit which button, I give you the code corresponding to the button. Sounds fair, doesn't it? What happens if I hit 2 buttons at once? See, this is the problem. Decoders are well defined. Encoders are not. The reason why a decoder is well defined is you give me a code, right? You can't give me 2 codes simultaneously, so there's only one output line I can ever turn on at a time. But if I allow you to pick codes, what's to stop somebody from just hitting all the buttons at once? Right? And then which code do I put in? Now, these are kind of some of those unexpected little things, right? You've got a well-defined thing, you flip it, and it becomes pretty unwell-defined. Just a quick side note, This is actually a reason why you want to have all kinds of random inputs when you're testing stuff too. When I was going through college, my roommate was an English major one year when I was going through digital logic, actually. And, I used him as my test bench because there was no better test vector generator because he'd start flipping things. They'd get bored and just start hitting stuff, right? And he would generate weird errors that nothing else in the universe would. But I don't know how this guy could be that. I knew how you're supposed to treat the electronics, so I treated the electronics right. He'd just go slapping stuff, and you'd get weird errors that'd creep in. That's actually what you need, right? We are like the worst testers in the universe because we know what our equipment is. It kind of almost deeply offends us when somebody hurts the thing we've been building. It's like, hey, I've been working on that. I've been pouring my heart and soul, and you're just slapping it, right? But that's what your end user does, right? Your end user drops things, kicks things, all kinds of other stuff, and they expect it to keep working. You're an engineer. Build something good, right? So my encouragement to you is exactly on this type of a problem, right? It wouldn't at first be obvious that that's the case. Right? So you really need to get somebody who's going to really smack it around and do things that you would consider crazy and dumb, that wouldn't even enter your mind because you just know how to treat electronics, right? So there's a lot of different things that are out there. I kind of sometimes call it the English major, testing system, or, maybe that's not as polite now. You can pick whatever you want. I've heard people say, find the person who is the klutziest person to test your things. There's all kinds of ideas, but that's really what you want. You want the person who's going to do unpredictable, crazy things, because they will generate the results for you, and you want those early so you can bulletproof them. So we don't actually ever build an encoder, but we do like this idea. So what we build is what's called a priority encoder. The difference is a priority encoder sets which of these codes is most important. So if you give me multiple codes, then I'll know which one to pick. Okay? We often, with this one, potentially have an enable also with it. I'm going to ignore the enable at the moment. We not only get this, though, we also will get one extra one now. All right, so this will be our code, but we'll also get another one sometimes called V. It stands for valid. Because there's one other screwball-y thing that can happen to you here. All right, I could say, hey, can you test this, put some voltage down the line? Well, what's the first thing that happens? They think about it so they don't put anything down the line. What happens when no code is set? Well, if I allow a 0 down here, that would mean this code was sent. I don't have a code in my codes for you didn't send a code. So I have to give you something else that says you didn't send a code. And that's what valid is. All right? Valid means you sent a code if it's a 1, and a 0 if you did not send a code. That way you can tell the difference between 0 and not 0. The same trick is going to happen because remember, these are all tied in with memory. When you get to comp ord, you're going to have the same exact problem when you deal with cache. Because cache, is kind of like a storage of memory, really fast, close by, things like that. You'll load your data up and put it in this cache locale. But how do you know you've loaded something in or not? Right? Because the cache locale is always going to have some number in there. Right? Because it's 0 or 1. There's no possibility to don't put a number there. Right? I can leave a blank, but the computer can't. It's got to have a voltage. So what does it do to tell you nobody's loaded anything in cache yet? Well, each of those locales has to have a valid bit to tell you whether or not something's actually occupying the memory. Have you used that piece of cache yet? So this same exact trick is going to happen. All right. So for this one here, we're going to take our inputs are now this 0 through 3. And my outputs are the code and the valid bit. I'm just going to put V for valid bit. Okay. Now, if no code is on, all zeros, the valid bit is off, and I don't care what code you sent, because the code bit is irrelevant when the valid bit is off. I'm going to make the one on top here my most important. You can pick whatever you want, but most people start with 0 as your most important. So we put a 1 here. If this is 1, I don't care what the other ones are. The code is going to be 0, 0, and it's valid. That's my priority. 0 has my highest priority. If 0 is a 0, but 1 is a 1, it has higher priority than the others. I don't care what they are. The code will now be the lowest number, so 1, and it's valid. Same thing. If these are both 0 and that's a 1, 2 has a higher priority than 3, so I get the number 2, and it's valid. If all 3 of these are a 0 and this is a 1, then you'll get 3, and it's valid. So this is kind of a truth table for a fairly typical encoder system. Sometimes these bits, and with here, sometimes the inputs and the outputs are inverted. Doesn't really matter, right? You just have to look at the table to see. So sometimes 0 is the signal it wants, and 1 means nothing's there. It just matters, are you high or low voltage as your default. Okay, is this good? So how could I get with this system what this signal would look like? I just do Carnot naps, right? I got 3 of them here. That's one way I could do them. I could just walk in. These mean run through all the possibilities. These mean truly don't care. So for instance, I could take this very first bit of my code here. I've got 4 different ones here, so that's going to be your kind of standard Carnot map. Zero, 1, 2, 3. Now I have to be a little careful because these are all kind of in jumbled orders here. And so for the first one here, everybody's 0. That's this little upper square here. All right? I don't care. If 0 is true, I want a 0. So if 0 is true, I want a 0. It doesn't matter what anybody else is. I want a 0. So just fill them all in. See how that works? All right. This is a 1. Who cares what those are? Just fill them all zeros. All the rest of them are filling the rest of this where 0 is off. 0 is off, but 1 is on. That's this column here. All right. 0 is off. 1 is on. I want a 0. Zero is off. 1 is off. 2 is on. That's these ones. And in that case, I need to get a 1. Final one here. 0, 1, and 2 are all off. 3 is on. That's only this square that hasn't been filled in yet. It's also a 1. This one's a don't care, so the best thing I can do is just circle up the side here. And I find that the most significant bit of the code, right? Code bit 1 has to be equal to this encirclement of 1s, which is not 0, right? And, or sorry, not 0, yeah, and not 1. That's this encirclement. We agree? So this tells me how to build the first column. I do the same thing for the second and the third. I get 3 functions. That determines my 3 outputs. All right, and then I would just build that function. That's a single AND gate. It's not bad, all right, to do an encoding. That make sense? So the book goes through the whole thing in detail. I think they do it with 1s instead of 0s. I think they flip the code bits, but realize it doesn't matter. All right? They're done in all kinds of different ways all over. What I really want you to do is understand the idea and realize you can build whatever you needed out of them. All right. If this makes sense what the codes are, what can I do with these things? All right. So let's consider for a sec, you want to convert, or you're given the problem to convert, let's say, gray code, and let's say it's a 2-bit gray code. Gray code 2-bit. And I want to go to binary fine for this one. Binary 2-bit. Does that make sense to the thing? Okay. So what we're going to do on this is we're going to consider our codes for this. The gray bit 2 code looks like 00, 01, 11, 10. 2-bit binary is 00, 01, 10, 11. This I just put them in numeric order. Okay? So if I want to convert from gray code to binary, and I get a 00, I want to output a 00. If I get a 01, I want to output a 01. If I get a 11, I want to output a 10. And if I get a 10, I want to output a 11. Does that make sense? That's what we just mean between those 2 codes. And that's what it means to convert between those codes. Now, I could go through and I could build a truth table and all kinds of other stuff and do this. But I could also just go, well, heck. I've got a decoder here, 2 bits. And I stick my gray code on it. And here I get 00, 01. But remember, it's going to be in binary order. It doesn't know what this is. It just knows it gets a pattern that comes down it. And it'll light up one of these lights or power one of the lines, right? On the other side, I'm going to put a priority encoder. And what's going to come out of this will be binary. Now I just have to hook them up. 00 should go to 00. 01 should go to 01. 11 should go to 10. 10 should go to 11. Done. That converts gray code to binary. It's real easy. I just have to list the codes and say which ones go to which. I pick this code on this side, and I hook the appropriate one to that side. Here, when I'm writing the codes, they're obviously all in straight order. Here, I got to find them in the order that binary would have put them. But it doesn't matter. This one would send in a 1-1 code when it means to, and that would get bounced, right? That line comes in, it comes over to here, it turns on the 10 line, and it sends out a 10 code. That's how it works. All right, now this is nice on this size, but remember, these things can get as big as you want them to get. So I can handle significantly larger codes, and all I got to do is connect a wire between them. That's like drawing little lines. All right? So that's a very easy way to generate decoding circuits. So if you have to decode signals, almost always one of the best ways to do it is doing one of these decoder-encoder pairs. Because it is as easy as just, this code here goes to that code, this code goes to that, this one goes to that one goes to that one. It doesn't matter how big it is, just march through the codes. You'll notice on some of the homeworks I make you do this thing, sometimes I even give you codes that you haven't heard of. They are technically in the book. You could also just look them up on Google. My point on this is it's completely irrelevant what code. I could give you the most obscure code in the world as long as you have the ability to look it up. It'll take you a few seconds to do it. You pull up the code, look what their pattern is, match it to the next one. That is all you have to do. And what I want you to learn from that is it's irrelevant what anybody gives you. You can handle all codes equally easy, very fast, hardware implementation done. So somebody gives you some strange code coming in on an input line and you need a fast solution of it. You don't have to write it in software. You can just do it real fast. It decodes it, sends it to your inputs of an Arduino or something, and just let it go ahead with binary then. Okay. So this is why we can, for instance, use gray code on a lot of our input devices, because we're trying to get the nice, fast and error-resistant properties of gray code. But binary is much better for calculations on the machine. I can build a real simple converter right there at the actual, my discrete unit, and I'm done. We feel comfy? Okay. How many people have used oscilloscopes? Have you ever had to take multiple channels and display them on the same thing? So they had this mux setting. What was the mux setting? You could let multiple things come down the same line. You just time shared it, right? You could switch between them, right? So an oscilloscope is one way. Another way to think about this is, imagine I had a train tracks. My kids, when they were young, loved Thomas the Tank Engine, right? So you had these kind of like train track things, and they had these kind of like little units that kind of went like this. And then you could hook on whatever other train tracks you want going off, right? And you kind of drive down, and your train could drive down whatever unit you wanted. Then they had the really fancy ones where there was like a little switch over here. You could push it, and it would open one or close the other. Right? I'm seeing some people nodding. Right? I mean, they were kind of old wooden train sets, but amazingly fun. Anyway, a mux is this right here. It is that train track switcher with the fancy upgraded switch that forces you to go down one line and not the other. That really is all it is. All right? So you can imagine if I have an electrical signal and I have a mux, and then we have a code which says which line do I want to send you down? Line 0, line 1. And you have some signal X here. So if on this line thing I set 0, X goes down here. But you could switch it at any time you want. You just change the value of this line, and all of a sudden X goes down the other one. All right? I just drew that completely backwards. I just realized I drew that backwards. I'm sorry. So I'm dyslexic. I draw things backwards all the time. I'm sorry. All right? Mux should go that way. Train tracks coming in, stuff going out. My bad. The other one, that's called a demux. This is mux. All right, for multiplexing. So anyway, we have a line number here, and it just picks which line you go down. Right? So if I pick line equals 0, in it goes. The original idea of this was I could have at one end like a whole bunch of stuff, like all kinds of peripherals off. And I have a chooser which says who gets to talk on this line. And then I have another thing here on the other end who's the listener. And I get to say who on this side gets to hear it, right? So I have a selector. So if you imagine whoever is here wants to talk to this one over here, I just set the appropriate code right here to connect this one to the destination one over here, and I can connect anybody up I want to connect up. What that makes this is a bus. So if you think about it, anytime you hear a bus, this is basically what they're doing. Okay? This is a centralized system to handle it. We'll also talk about a decentralized one in a few secs. But a multiplexer and a demultiplexer, the multiplexer sends you onto the bus, and the demultiplexer takes you off of the bus and sends you to where you're trying to go. Okay? That's the whole idea of multiplexers and demultiplexers. Okay? So far, so good? All right. So if you think about this idea, right, the most useful one turns out to be this. Multiplexer is going to become your best friend in the universe, right? It is actually for things, as much as everything else we've talked about is like really useful, multiplexer is going to be crazy useful, right? We will keep coming back to it again and again and again. It's one of those kind of utility knife things like an XOR gate, right? It can do many things you want, and when it does it, it's stupidly elegant. Right? This multiplexer, this generation of a bus, not only is good when you're building a bus, right, or its distributed version, but it turns out it's really awesome for when you actually have to build, say, for instance, implementing a function or things of that sort. So let's just talk on a smaller scale how we might build one of these. All right. And then we'll show how we can use it. 0, 1 output. And then I have a selector. Okay. All right. So what we want is, we've got inputs, we've got selector, and we've got 0, and we've got 1, and then we've got our output. Okay, if the selector is 0, okay, then whatever is on the 0 line, right? This could be 0 or 1. I don't care what's here. The output is going to be whatever is on this line, 0, 1. If the selector is a 1, I don't care what's on 0, I only care what's on 1. If it's a 0 or a 1, I will get a 0 or a 1. That's how it works. Now notice, this is again not your usual order of truth table, but you'll see that it's fairly common that people often give you kind of the why it works or how it works type of version of it. I am covering all possibilities of them, right? Because if you look at this, this is both 0 and 1. So you'll get 0, 0, 0, 0, 0, 1, right, so on and so forth. So we'll walk through all the possibilities, right? 0, 1, 0, 0, 1, 1. So it generates them, just some of these lines will have to get copied multiple times. All right. Now I can obviously take this and I can implement this in two-level logic. Do we agree? All right. So let's just, sometimes in the past I've drawn these. I don't think it's actually all that useful, right? As long as you know I can do it in two-level logic, and I will do it in two-level logic, that's really what you need to know about a mux. That anytime you see a mux, it's 2 levels of logic. The more important thing to a mux to me is actually understanding the implications of why this works and what it means. So this selector, let's try to put it in English. Right? This is saying if the selector is 0, then the output will be the same as this. Else, if it's 1, it'll be that. Guess what construct we're building? This is an if-else statement. whenever you write an if-else statement anywhere in your code, it forms a mux. Remember, anytime you write Verilog, it builds something. Well, one of your major constructs is an if statement. This is what it builds. You can always write any if statement as basically a mux. That's huge, right? Think in your programming, how often you use if statements. Beyond that, right? So I could get, if you get a bunch of nested if-then statements, it's just a bunch of nested muxes. So it forms a tree, right? So you could easily connect them together and see how they work. So a lot of code works that way. If I want one bigger than this kind of binary state, so you have multiple selections, that's just what would be, we would call in Verilog a case statement, or what you would call in C a switch case. Those ones will also form muxes, they'll just be bigger muxes. So if-else statements are 2 input muxes, and case statements are larger muxes. So 2 of our big programming constructs end up turning out to be these multiplexers. That's kind of neat, right? So first off, it gives us a really good equivalent because we can write a lot of code, and this tells us how to build them. Option number 1. So number 1, it's an if-else. Number 2, it has the dead coolest design technique, right, that you can do for implementing a function. This one's kind of crazy cool. So let me take some function, whatever, A, B, C. All right. Give me your function f. I don't care what you pick for. You guys have a preference? 0, 1, 1, 1, 1, 0, 0, 0. Fair enough. All right. Now this would be, I mean, it looks like they're all clustered together, but they're just offset. So it's actually kind of an ugly looking pattern that's in there. But here's what we do with the power of a mux. I'm going to group them together like this. I'm going to break C off. So the last one. A and B are going to become my selectors. So I'm going to have a slightly bigger one. It's going to have 1, 2, 3, 4 inputs. So this would be just written as a case statement. I've got 0, 1, 2, and 3. My selector has 2 bits to select between these 4, and that's going to be AB, which I connect together with curly braces. All right, now here's the cool part. Here's 0, 0, that's 0, 1. Notice that 0, 1 is the same as C 0, 1. So I just call this C. I want to pass C through to my output. How about here? You see a 1, 1? What's that pattern? Oh, it's always 1. Hook power to it. Right here, at 1, 0, I have 1, 0. Well, that's the opposite of C, isn't it? That's C prime. At 1, 1, it's all zeros. That's grounded. So what I do is, when this right here, 0, 0 case, I want C to go to the output. Well, when it's 0, 0 here, this goes to the output, so I put a C hooked up there. At 0, 1, 0, 1 here has 1 go to the output. I'm supposed to put a 1 there. When AB is 1, 0, that's going to be this 2 will be connected. So I'm going to hook C prime there. And when AB is 1, 1, this one connects to the output, and I want it to be all 0, so I ground it. Function F, I'm done. Now this is the neat thing, right? This had a total of 8 lines, but it only took 4 to build it. That's, I mean, honestly pretty cool in my book, right? This is like one of those darn niftiest little things. It's really stupidly easy to build. It's really easy to put this into Verilog code too. Inside of an always, right? Always at star, build combinational logic. I just do a case statement. Case. And what am I doing my case on? Well, A, B. Right? That's here. That goes in the case. Remember, it's not switch case to us, it's just case. So case, that's the selector. And then the individual cases are listed. This is 0. 2-bit binary 0. Colon, what should I do? F should get C. Next one, 2-bit binary 01. F should get 1. Right here, 2-bit binary 10. F should get not C. The final case. I could list its number, but you should say default. Right? Because there are other possibilities. Right? I could get a short, I could get whatever. Whatever you want to handle all those weird cases of a short or an open circuit, somebody forgets to plug a wire in, right? You make that. If you have no better choice, you do the last one in the list. If you have a better choice for what you want as a default, pick that. And then in this case, I want F to be 0. Now notice the 1 and the 0, I could also just have put 1-bit binary 1, and I could have put this one as 1-bit binary 0 if I felt like it. All right. When it does this, it actually builds 32 bits with those values, and it takes the rightmost. So it actually does the same. No, it doesn't really matter. But if you want to be, really technical, you can put those in. I just do an end case. This is a single statement, so I don't need a begin end around it. And I'm done. This is actually going to implement this right here. It gives me a very nice, elegant way of doing it. So this gives a very, very powerful circuit for it. That make sense? So this is why I say a really awesome way to implement functions. We'll do another example in a few seconds. I just want to make sure I get through all the different variants on this. So one final thing that's useful is when we get to the memory section, this is useful for what we call states. Has anybody started CompOrg or have you done 3336 microprocessors? Not yet? Yeah. So you don't have to. It's just in those courses you'll see where this example goes. I'm going to explain real quick kind of the basic thing that how a computer operates. Right? So a computer has to take the instructions you write. It has to figure out what that instruction is and then do it. Right? So what we have is what's called a fetch cycle or an ifetch cycle, instruction fetch. It has to go out to memory. It has to grab an instruction. Right? So that's the first step it does. Right? Its first state is go get the instruction. And then the next state it goes to in the next little cycle down the line is it does what's called decode. Figure out what this is and get all my data for it. All right, so it might be add and add these 2 different values. So it has to go grab those values, right, and get everything prepared. Then it'll do what's called execute. It'll do what you told it to do. And then it'll do what's called write back. It'll take those results and store them wherever you said to store them. And that goes back to the start and does it again. So there's kind of 4 steps it has to walk through continuously. Well, that's what these are states. Right? I can take these 4 states and I could have everything you're supposed to do, all the signals that set up the instructions to go fetch it. I could hook all those wire things in here and put them on so that at fetch this happens. All right? And then at decode, I set everything up in here, and I have just tons and tons of these. It's switching, but it just switches them all during that state. All right? And so on here, execute right back. And it just literally walks through those 4 states, sending those signals to the appropriate ones. It's basically the entire cycling of your computer is basically a whole bunch of states you're walking between, and each state can be implemented as one of these mux levels. Just make them a separate state and away you go. So basically you use this thing for building all these fancy state diagrams. Okay? And they're a real nice way to implement computers and all kinds of stuff. So when you get to those courses, you'll do a whole bunch of stuff with muxes. That make sense? So these 3 right here are why I say, you know, mux is going to be your friend. It solves a lot of stupid problems. Very, very useful. Okay. We good with these? Do we want to do one more implementation? Or do you feel good with it? One more. Awesome. Do we want to do a bigger one?
Sure.
4 big enough? A, B, C, D. Awesome. Okay, I just set up my truth table first. All right, you guys pick. What do you want for a function? I mean, I obviously picked the other one so I could walk through every example. So, but I don't want to, so that was kind of like cheating. All right, but I wanted to give you one that had everything in it and that was small, and that's the smallest one that elegantly does them all. So, I'm going to let you pick.
1.
0.
2, 1, 0.
0, 0, 0.
1, 1.
0, 1, 1.
Okay. Now notice, I mean, I could obviously fill them all in, but I always suggest you do everything in these kind of groups, and then the last one is the only one that doesn't. Because we always take whatever is the last one on the right, and that's going to separate off. This is my address part, and this is my input. Just to make this even more obvious for them, this is 0, right? All zeros. 1, 0, 0, 1, 2, 3, 4, 5, 6, 7. All right, the address is ABC. It's 3 addresses to pick them up. My output will be F. Now, all I do is I walk through, and I'm going to pick this to be one of 4 things. It's either got to be 0, 1, D, or D prime. It's the only possibilities. It gives you every possible thing. I just look at them 2 at a time. 1, 0 compared to 0, 1, this is D prime, which means this is D prime. Next one. 1, 0 again, D prime, D prime, right? You can just see it's the opposite of D. The next one, both zeros, it's a 0, so that's got to be a 0. Right? 2, 2. You guys help me out. How about 3? That is D, so I put a D here. How about the next one? 1. I put a 1 there. How about 5? Yep, it's D again. How about 6? It's 1. And how about 7? Look at that. Look how easy you built that. See what I mean? It's like crazy elegant. Right? And you're done. All right. We feel good with Mach's design? Yeah, I know. It's like when I saw this, I'm like, dang, why don't we just only do that? The reason is, no, it really, I mean, whenever you see something elegant, you have to answer, why don't I do this all the time? Right? But we just like to cause you pain. No. This has absolutely no safety factors. Right? This is glitch prone as hell. But if you're building an FPGA, it's synchronous. So as long as you meet the clocking requirements, it'll never see those glitches. So who cares? I'm now safe again. So this is why we love this in FPGAs and anything that's highly synchronized. Right? As long as you meet the timing requirements, you're golden. Right? So then you pick whichever one's most elegant. Right? A lot of the other ones, like the encoder decoder, is really good if you have individual components. And there are times you'll see, like, you buy something from Arduino and they'll have a whole bunch of little specialized components on the board that'll quickly do something. Well, things like encoder, decoder are great little, you can get little tiny surface mount devices to just build those, right? And they'll fit really nicely on the outside and you're done, right? So there are a lot of things like that, particularly for input and output. You want discrete components, and some of those other ones are easier for that. Okay, well, if we're good with this, the one thing I could say that would make this better would be if I didn't have to build the whole thing. I could just take piecemeal just what I wanted. And imagine this is like a bus, and here's a bunch of devices. I don't always stick like 8 devices right by each other. I kind of have one over here and then one over there, and I want to kind of separate them out. Does that make sense? All right, so I want a way to get onto a bus that's one at a time. This is what we call a tri-state gate. It's basically something that connects you or disconnects you in one location. So we draw it just kind of like a buffer, because it is. It's a buffer going onto a bus. This side is the bus side. This side is my signal. But it's not just any old buffer, it's a controlled one. If this control is high, a 1, it'll let the signal on. If the control is low, a 0, it'll disconnect you from the bus. So that word is really important. It doesn't send a 0. That's not disconnect. That's sending a 0. Disconnect means what? Like pulling the wire, right? You get a Z, the high impedance state. So for us, we've got the control and we've got the signal. And then what's going to go out on our bus was the bus C. If my control is a 1 here, the signal could be either a 0 or 1. The bus will see that 0 or 1. Just basically the same exact way we talked about our Machs for the different levels. Except here, if control is 0, doesn't matter which of these it is, it gets a Z. Now I could therefore just set up one of these for each of the levels of my Machs, and just make the control signal the output of the appropriate AND gate from a decoder or whatever. Right? And then it would turn just that one on. The other ones would be off. They'd be disconnected. So only that one would see the bus, and it would go through without any interference. Because the other ones are just not talking to the bus. They're electrically isolated. Does that make sense? So this really is just a fancy way to kind of build this. Now, this has an awesome device for implementing it. This is the smallest, fastest device you could ever see. It is one transistor. We literally build this by having a single transistor. Here's your signal, here's your bus, and here's your control. It is one transistor gate. Because if I apply a high voltage here, it's going to connect these two sides. Remember, you already kind of did this for BJTs. Make one flow, you connect them. All right, same thing happens, similar to FETs, except it's just a voltage. It's not a current being applied. So I put a high voltage here, they connect, it sees it. I put a low voltage here, they're disconnected, might as well be separate wires. Done. Right? Really, really fast, really, really easy. So this is kind of a very nice setup for doing this. What if I don't want to have the control be a 1? What if I want it to be a 0? Well, you've got the other FET. Low voltage connects it. All right, because remember, we got two different types of FETs, just like two BJTs. All right, so we have a second symbol here. If we put a bubble next to it, it means a low control lets it on the bus. Without the bubble, high control lets it on the bus. The way you specify this device inside of Verilog is buff if 1. That builds this device. So that's the command. It's all one word. Buff if 1. If you want the version with the little bubble on it, it's buff if 0. All right, so I could say buff if 1 Fred, right? And Fred then has several inputs. It's got, right, whatever its output is, and its input, and its select. But that's it. Same thing with buff if 1. Remember, output's first on official stuff. So that gets you through basically the last of our devices, right? And how you can implement them inside. So my plan is next time we're going to just talk all on Verilog and how can we do testing, because we haven't really talked about, better ways to do testing, other than we've mentioned a couple things like make friends with an English major. Probably shouldn't tell them you want them for just smashing stuff, but hey, maybe we'll make them happy. I don't know. But we'll talk more in depth. How do we build this in ways that's kind of more systematized? If you have questions, as always, welcome to have you up here. Otherwise, have a lovely weekend. Man, I burned the pages here. Oh yeah, and I'll set up our.
I had one question.
Sure.
As we were going through the, what part was this on? The priority encoder, how did you take this truth table and take it into a Cartesian map?
Oh, sure. Yeah, let me just.
Yeah, it might be easier on here.
There. Okay, let's just do a new one in green. There.
Perfect.
So we've got 4 of these inputs. So that's how we knew that we get the K map. And just remember, it's Carnot, not Cartesian.
Okay, K-map.
Yeah. All right. It's a dude's last name. Oops. Let's look down here. That one over here. 0, 1, 2, 3. Okay. So we look at this, right? This is a truth table. It's just in a weird order.
Okay.
Does that make sense? So this is when 0 is off, 1 is off, 2 is off, 3 is off. So 0 is off is this side, 1 is off, is, and 0 is this column.
Okay.
2 is off, and those are this, and 3 is off. That cuts me down to here.
Okay. And
Right.
then we get an output of X.
And so we take, let's do the second one just to make it interesting, right?
Okay.
So we put this X here. So
Okay.
we'll walk through in green, and we'll do this one.
Okay.
All right. So I go to the next one. 0 is on. Well, 0 is on in this whole side.
Oh, we don't care about.
And we don't care what those ones are, so it's all of this side.
Okay. And our output.
And
is
so it should
0.
be a 0.
Okay.
Then this is a 0 now, so I'm on this side again. But 1 is on. That's here.
Okay. Okay.
All right. And so that should be a 1.
Okay. That's making sense now.
Okay? And then I've got both of those are off. I'm in this column. 2 is on, so that's just these last two elements. And I should get a 0.
Gotcha.
All 3 are off. I'm up here. But 3 is on. All right.
Okay.
So now I've got this 1.
Okay. Thank you. That makes sense now.
All right. And so in this case, I'd circle that one and this one.
Also, you can't circle groups of 3, right? Like
No.
if it's 3 in a row.
It's got to be powers of 2.
Okay. All right.
And the lengths and the widths have to be powers of 2 also.
So you can't
So
circle.
it has to be a 1, a 2, a 4, an 8, so
Okay.
on.
So like if there's like 1, 1, 1, 1, 1, 1, you would have to do 2, 4, 2 4s.
Yeah.
Okay.
Exactly.
Okay. Thank you.
You are welcome, sir.